Okay, so I propose that we restart, and sorry to interrupt all your exchange and the discussion. I know you are a bit frustrated about the fact that probably we have not allocated enough time for exchange and networking, but well, at least at the end of the meeting, we will offer you a light lunch, and it will be also, you will have plenty of opportunity then to continue your discussion. So now we are going to move to the next part, another session, I would say, of this workshop, which is organized to also to get an opportunity for those who are really offering the solutions, and basically that's their business. So it's not necessarily for free, but they are really offering nice solutions to implement this approach. And the first one will be CITRINE Informatics. I don't know if you say CITRINE or CITRINE. Marius,
CITRINE.
Tell us.
CITRINE, that's the name.
Okay.
Pronounced it perfectly.
And so we have the pleasure to have with us today, and unfortunately he was not able to make it physically in Grenoble, but I saw that it was really interesting to have him with us, even if it's only through Zoom. So Marius is the director for Europe, Middle East, and Africa at CITRINE Informatics. And so the floor is yours, Marius.
Merci, Philippe. Thank you very much. Apologies again for not being able, especially as an INP Grenoble graduate. I mean, the Grenoble feels like home to me. So, well, again, I mean, thank you for the opportunity, Philippe, Gemma, to share some of our thoughts and our view, especially from an industry vantage point, about how AI is being used today and some of the benefits, trade-offs, some traps of going down the digitalization path, and humbly maybe a recipe for potential success deploying it in the mainstream of the industry going forward. So a couple of things that I wanted to cover. Again, why companies are using AI as of today for their R&D, some of the tangible results, kind of an ROI-driven and KPIs out of this usage, the approach, what makes it successful, and we'll be talking about things related pertaining to projects, pertaining more to organizations, and overall as more of a philosophical, strategic decision to migrate, to digitize and automate R&D processes. And with a bit of chance, we'll have time at least for one or two questions. Appreciate time is short. So without further ado, the company, I mean, we are leaders in the chemistry and materials development space. 9 years ago, we started this company with a vision of bringing the data at the forefront of development of materials and chemistry. And we developed at the time the first chemistry-aware material informatic platforms, right? That's plethora of ideas, and we've heard very interesting concepts and very interesting initiatives across the board within the industry. Our mission has always been sticking to this concept of building a self-contained yet open platform, SaaS platform, to accelerate the development time for our industrial partners. We're talking about industrial partners, but obviously we're very active in the academic space as well. Our founders come from academics, and we have patents, obviously publications, and some number of high-profile industrial and academic partners. We'll be mentioning a couple of them in the next slides. So when we're looking broadly at the industry, right, overall, our platform, AI, is being used across a pretty large panel of applications, right? Being polymers, being alloys, solar materials, glass, batteries is a very hot area, as you've heard it from my fellow partners, I mean, who presented before me. So AI is becoming pervasive across the industry. Whether the adoption is where we want it to be, for sure not, that there's a lot of room for improvement there. There are very good reasons why the industry is a bit lagging behind our other industry in terms of automation, right? Data sparsity is one question. The very experimental driven sort of R&D is another, I wouldn't say a problem, but it's definitely something we need to encompass with and work with. And you'll be hearing, I mean, from us how we develop our platform, right? The AI platform to work in this particular, very peculiar domain, right? The chemistry materials space. So one thing that is pervasive across the chemical and materials industry is the scarcity of data, right? Data is expensive in our space. We do not have the privilege of working with tons, terabytes, petabytes of pictures that we incorporate, throw into a black box AI machine and just crunch the absolute phenomenal outputs that everybody would expect. We took a different approach, right? In our space, we can work with as little as 25 experience, right? I mean, let's put it this way. We can work even with 0 experience start. Ideally, there should be some historical data, but we can work with simulation data, sort of engage the effort of building models. Once we have this data, the starting point, we start practically building AI models, representations. This being a chemistry-aware platform, we can understand direct molecular structures that are converted to Smalls notation, and in turn, they end up into descriptors, right, for our models. And all throughout this process, again, this not being a black box approach, we work with scientists. We work with our customers' teams to guide the creation of the models, to guide the improvement, right, the sequential improvement of models. And typically what we do, we end up looking at the philosophical problem of the proverbial challenge of finding the needle in the haystack, right? What we typically do with our platform is help scientists and engineers identify the proper haystack to look for that needle, right? For complex formulation, this tends to be a very huge design space. So investigating this design space, finding the proper candidates and scoring the candidates, that's something that we do with our platform, right? As opposed to this non-linear, a little bit hectic DOE approach that has been the common thread throughout the industry. We come up with this data-driven, scoring, error-rated candidates and methodology, right? We don't eliminate the experimental steps. It's not our goal. I mean, we don't have a magic button that gives you the perfect golden candidates in the first trial. What we do is typically we reduce by a very significant rate the number of experimental iterations, right? By taking this data-driven approach, the sequential loop that improves constantly the models, as well as decreases the error rate for the candidates that we generate. All throughout this process, the skill set of scientists and engineers is vital for the success of the project. So that's our platform. That's what we do. And you know, you've seen a certain number of industrial partners who are using it. Some of the people in the room are partners of ours, and we're happy to count them as customers and partners. But typically, what are the main threads in the industry? Why people are using the AI? I mean, one bucket, the first bucket would be to improve the performance of their formulation. I mean, it's where we're preaching to the choir. You've all been exposed to more and more demanding specs for your formulations. A lot of people are going this space. The second bucket is accelerating the product development. Time to market, vital in every industry. Chemical and materials industries are not indifferent. And the third bucket is more of a, let's say, structured, thoughtful process of increasing agility, right? There's closing this agile development group that goes from the customer demand to being able to speed up. And we heard from the Solvay friends and BASF and Dow, the need to be very close to your customers and accelerate and make sure that you can guide them throughout their requirements and offer them solutions from the very initial steps of the engagement. So just sharing a couple of very concrete examples from our partners. So in terms of improving formulations, I mean, this is one large plastics producers. You've seen the logo in one of my first slides, who wanted to reduce the density of a polymer formulation, right, while maintaining the mechanical performance, practically, getting the weight down. A new market for them, protecting against competition. What they've done is that they incorporated all the historical data, new data that they had, as well as the domain knowledge that they codified into our platform being capable of integrating this contextual information on top of the raw data ingestion. And they ended up actually improving their formulation. What is particularly striking here, they reduced by 60% the development time, right? And ultimately added a couple of millions per year to the bottom line through this process. I was mentioning the more of an accelerated product development time, and here's another example that may be relevant to you. This is Ubiquitous Energy, a very fast-paced, dynamic company in the US in the solar space. What they were trying to do is literally screening new molecules, right? And screening molecules, tens of thousands of molecules may require years through a typical DOE approach, or counting on the luck or the absolute expertise of the scientists to hopefully get to the golden candidates. What we've done is practically accelerated by 10x, and this is our partner estimation. The time to find these molecules and improve the accuracy of the models. Overall, I mean, if we're talking about larger projects, right, and how you can use AI to practically from the inception, from the get-go, with no knowledge whatsoever, upfront knowledge about a formulation that would get you there. This is an example for NASA. We worked with HRL Laboratories. Practically, I'm building an AI, an alloy for additive manufacturing for space applications. Typically, practically working with a design space, there was counting millions, tens of millions of possibilities, right? So we narrowed it down to hundreds of candidates that could be tested and bringing development time from years to days, right? That's one of the success stories that we're proud to mention, and where HRL and NASA achieved phenomenal performance there. Overall, if we are to talk about what would make it a success, I mean, adopting and deploying this, and it's, again, it comes down to three sort of main chapters there. One is project related, starting with a clear goal, right? As this being a data-driven, our partners need to know exactly what they expect, right? What they are getting to, what they are aiming to get as results. We need to have this structured approach. Data is important. You've heard it from my colleagues, my peers, hours ago. It's good to start with proper data. The more metadata you have associated with that you can incorporate as domain knowledge, the better, right? We can work and enrich this data, but data is still a good point to start. And ability to test results. Again, there's no magic here, no push button. You still need to take these candidates, go to the lab, and re-inject them into the AI platform to further improve the models. If we're talking about more of an organizational considerations, what makes it a success is the long-term vision, right? This is no cheap trial kind of approach. You got to make sure that whenever you're engaging this, you know exactly how the value chain works and how the ROI. The ROI tends to be more back-end loaded, whereas the effort is front-end loaded. You need to make sure that the data is relevant, that you invest in this. And obviously, executive sponsorship is vital to make sure that top down. And again, from a technology standpoint, we bring this domain knowledge integration to the platform, and platforms like ours are chemistry aware, right? We understand the language. We do not second guess information, science information. This is codified in our platform. In terms of, maybe just before we get to the question, in terms of data handling, in terms of ecosystem plays, we're true believers in ecosystem, right? We work, as you've seen, with academic partners, large industrial partners, but data security is sacrosanct, right? Until and unless our industrial partners decide to work in a more collaborative and open approach, we provide the highest level of security for their data, right? They can work in isolation in a SaaS platform with their data being protected, but absolutely open to more collaborations. Let me just put it here. Don't want to make it too abstract. Can we take any questions, Philippe?
Yes, of course. First, congratulations for your presentation.
Thank you.
And I don't know if we have questions here in the room yet.
Thank you, Jérémy Auvergnat from Unicor. Thanks for your very nice presentation. At some point, you compare your approach with DFT, and I really like that comparison, because generally those two approaches are either run complementarily or in parallel. The big downside, I would say, of DFT is that you will predict a property, but you will not always be able to synthesize the compound afterwards.
That's right.
Can you comment on your approach in that regard?
That's right. That's a perfect example. Let me put it this way: you can predict anything out of anything, right? If you work with very low data and no real information, domain knowledge information, everything is feasible, right, for an AI engine. What we typically do, and you're mentioning a bit this testability and feasibility standpoint, where information that are not typically codified in the regular databases, if we were just to ingest the raw data, you wouldn't have this sort of productivity, sort of implementation information, right? Feasibility from a manufacturing standpoint information. That's why we build a database so as we can work with scientists and incorporate this contextual information, this additional information as latent variables for our algorithms, for our models, to be able to train them and predict candidates that are as suitable from a scientific standpoint as well as manufacturability standpoint, if that makes sense, right? We do take into account this information.
Okay, another last one.
Thank you for the presentations. CITRINE is a part of a chain. You focus on the eye, clearly. But when you say we integrate data, we digest data, I guess to make things really moving, it's something that need to be automatized. So you plug, at one point you need to plug yourself to the systems, your platforms, to other systems. And up to, because AI is just, again, a part of a chain. So in terms of connection through the instruments, the tools, the data in an automatic way, and how the AI model deliver also to the users the result, and they can play in terms of interface, web application, and so. Can you tell more on the edge of the art of your applications?
Yeah, absolutely. Very, very relevant question. Indeed, I mean, we don't work in isolation, right? And data comes in different shapes and forms until and unless we get a standard, a common standard for data. We work, and our platform is compatible with the state of the art or regular sort of data lakes, all sort of databases, ELNs. We can ingest automatically data from these databases, and typically there's a lot of post processing that can be done, and we have data scientists who help eventually get data in the proper shape. Typically, if you have an Excel spreadsheet, at least that is consistent, the information is consistent throughout the data points, we can ingest it pretty much automatically. But there are, a wealthy range of APIs that have been developed, down upstream and downstream as well, because you may want to go. We have, one of my predecessors were talking about high throughput equipment, right? We can interface with complex systems to exploit the results and the candidates and go into a fast prototyping loop as well. So compatibility and IO's APIs are vital, and we provide this as well. Thanks for the question.
Yes, sir.
Okay, so thanks. Sorry, thanks again, Marius, for this very nice presentation. We will now move to the next talk with so presented by Johan Carlson, who is the senior industrial process scientist at Dassault Systemes. Well, you will explain us what is Beovia versus Dassault Systemes. Thank you.
Thanks a lot for the invitation. And I was a bit concerned when I got the invitation that in 15 minutes I should present all the things we're doing in digitalization. But fortunately, we had a brilliant presentation from the ISF from Umicore Solvay, showing how they build together. And basically, I mean, you could say we are the software one-stop shop to build all these things. So now let's show a little bit how this works. So we also were a small company from the beginning. We started as a spin-off from Dassault Aviation because it created CAD system that was so great, so they created a company from it. And the first real success was then when the 777 Boeing was completely done digitally first and then built. And then it has evolved with also the 3D PLM and then into the what now is called the 3D Experience platform, which is then a platform which is not just for part, but actually encompassing the whole process from research development into production. And so Dassault System is divided into 13 different brands which specific focus. And all these brands then work together via the 3D Experience platform. And I'm from Biovia, which is the most scientific part where we're doing atomistic simulation, taking care of lab data and also data science. And Dassault System is then covering also 11 different industries. So here out of random, I picked battery as example of what we're working. So the focus is then on transportation and high tech. And why are 3DS interested in batteries? Well, as we know, there's a large requirement on batteries, in particular for new materials. So I think it's a good example for showing how this new methodology is developed and used. And particularly, there's a big challenge for creating new batteries, because that's really the development bottleneck for the next generation of electrical vehicles. So we do have a lot of customers, so we can only recognize in the audience and also in the different levels of the development chain. So what is then the 3DX platform? Well, it is a platform which is intended to bring together the different parts of a company so that you can basically work together from the researchers doing really experiments in the lab, doing simulations, and that they can then post their data, which can then be picked up by other functions in the company. So it will move from being sending around emails and so this siloed approach, but rather that there is data. It's a data-centric approach. Data can be exchanged. There's a unified data model which can be used for integration. So that basically it has a social, a business, a scientific, engineering connectivity. And so I'll take then the example, apply it to battery research, because that's how we know each other. And we are then developing, or basically I should rather say, customizing the platform. We're using the platform to integrate from the development of batteries over manufacturing to also factory design. However, this is a pretty research-oriented meeting, so I will focus in then on the battery development. So we have this vision and plan where we are connecting the different parts of the battery from the materials or molecular level over the battery cell into also connecting more than one cell into a pack, and then even integrating it into a system. So here we have then 4 different entities within the company which are working together, and the individual solutions are really top of the market. But the real challenge we are facing here is now the integration of how we can use information and move that from the different levels of creating really a seamless multi-scale approach that we can really do materials development all the way down on the atomic level, connect that to a continuum 3D model, making simulations of an actual cell, and then also performance and engineering approaches to that, and how that also moves up the chain, how that could be the information about the single cell can be used to simulate the performance of the packs, and how that also works together to the actual final system. So I will focus in a little bit more than on the material side. So here's one example which we are working on right now, which is modeling the build up of the so-called solid electrolyte interface, which is the magic part of the battery cell. So what we need to do here is that we need to understand really the chemistry leading to this. So we need to break down the individual processes. So we build a process map. From that process map, we can then use that into atomistics, molecular dynamics simulation, and let the system progress. And from that, we can see how the system is building up. And then when we created an atomistic model, we can then go on and calculate properties for this model. So this gives us then information of an atomistic information of the processes in battery. So another example is then when we go from these atomistic simulations, calculating properties, in this case, for instance, conductivity, playing around with the formulation of the electrolyte, and taking that information and connect that to a system level model of a battery cell to do performance simulations. So by this, we can then play around, change the formulation, and do tests of what that influences the actual performance. So the focus of this meeting is really then the materials acceleration platform. And I think that we've been talking a lot of the role of AI, but I think that the real power in the materials acceleration platform is really a combination of all these three things: the simulation part, the lab data, and then bringing it together with the data science. And within this DASSAULT system, we are covering all these three parts. And now the challenge is, of course, how we can connect this in a seamless way. And we are working together. So Ivano presented the Big Map project. So we are part of that. And one of these things we are working very strongly on is on connecting these three components then into the materials acceleration platform, and really the big map. So that basically brings me to this summary slide of how we are developing our full life cycle model for batteries. So that we have on the we're starting really on the battery cell design from the materials innovation, and then we are working on getting that connection up towards manufacturing, so that we could basically have a digital continuum, and then also modeling the use of the battery. So here then finally also can say a few words about the challenges, and that is of course the integration between different length and time scales. So we have good solutions for the individual scales, and the real scientific challenge is bridging these scales to have them both scientifically, because I mean the science is not complete yet, and then there's also the technical part of it to also make a smooth data transfer. So about that, I'd like to say thank you.
Thanks to you. Thanks to you to have also to have been able to make it in the time. So that's great. So we have time for one or two questions again. Mario.
Thanks, very interesting talk. Speaking of interface, how far did you go to model the functionality of the interface, which is changing even during the life of the battery. So is it possible to model that and to put it in your loop?
Yes, you mean the SA interface? Yes, so we are working on, so I mean, I basically showed you the state where we're at now. So I mean, we have been able to simulate the early steps of the process. And yes, so the second thing is then calculating properties. I mean, we basically are ready now. So the since we have now created realistic atomistic models, then we can go on and do property calculations from that. So that's basically just the next step that we will try out. And I mean, what I should also emphasize is that we're also looking very much for collaborations here, because since we are completely theoretical, we also need to get the experimental feedback. So that's why we're very happy to be part of the big map.
And my question will also guide to this point. So of course, it's nice to simulate over multiple scales and multiple elements of a battery cell. But of course, you need at every point, you need validation through experiments. So what is your concept to really deeply integrate both? So experiments in the lab and to the simulation workflow?
Yes. So I mean, I could speak a few hours on that question. Yes. So I mean, on one hand, we're bringing those things together on a technical level, and then so since we have the lab informatics part and we have the simulation, so we can bring that together, but then of course we need a source of that experimental data. So that's where we're looking for partners. So basically, technically, it's that we're bringing together using our platform, and then on a more collaborative level, we are within the big map that we're, so to say, getting our contacts. Yeah,
but actually not yet on the data management side, but in the next version, we are more involved. And it would be really nice if we managed to have this duality of a physical process in the lab side by side with the simulation workflow, and make a semantic link in between. Would be really nice.
Yeah,
idea.
I mean, the semantic part is also very important, so that the information is also digestible. So I mean, just measuring is not really going to help us. I mean, it needs to be codified in a understandable way. Yes.
Okay, I'm afraid we have to stop here. Thanks again.
Thank you.
And so now we now move to the next presentation with a talk that will be given by Dr. Loïc Roch from ATINARY Technologies. I think Loïc, you are Chief Technology Officer in ATINARY and also a co-founder of this nice startup. I don't know how to qualify it. Is it still a startup?
Yes, it is. It is a startup. All right, great. Thank you very much, Philip, for the introduction, and thank you also for the invitation. So yeah, my name is Loïc. I'm the co-founder and CTO at ATINARY Technologies, and what we do is we develop software to accelerate research and development through the use of machine learning. So we heard about this all throughout this morning. Materials, of course, they are key for technologies across different sectors. But today's with current method, let it be high throughput experimentation, design of experiment or trial and error, is slow and expensive. And therefore, we need to rethink the way we come up with new materials and the way we optimize various processes. So before explaining the way we do it, a few words about ATINARY. So we are a Harvard spinoff. We were founded in 2019, first in the US, then moved back to Switzerland. So all the development is done out of the Swiss office. We develop a market-leading machine learning algorithm. I'll show you a little bit about this part and show you some results that we obtain with our ML algorithms. And we package the whole thing into a software platform that we call SD Labs for the self-driving labs. The platform allows to do ML and data-driven iterative closed loop processes in order to replace the trial and error approach or high throughput experimentation or DOE. The platform is built by scientists for scientists, and the goal is really to have a no code with and no ML expertise required in order to deploy the technology in your different processes today. And of course, the goal of this platform and this set of tools is to come up with better molecules, better materials, higher productivity, have a better return on investment, come up with discovery much faster, reduce the time from lab to market. So how do we do it? So we've seen a little bit about this loop, so I'll go through some of the detail of this loop. So what we do with SD Labs is we have a data-driven approach that is a closed loop optimization strategy. And the first step is where a lab technician, a scientist can log in on our platform through our SaaS software to define their objective, define also the parameters. This includes discrete variables, categorical variables, or continuous variables. We can also do multi-objective optimization. Once the whole setup or the whole process is defined through the platform, then the user can simply hit start, and then the machine learning algorithm will start to generate what is the next best experiment to perform. Once this experiment is designed by the machine learning algorithm, then we connect to the lab. So if there is automation in the lab, we can connect directly to the lab to make the whole lab fully autonomous. Or if the process is not automated yet, and if there is a chemist running the experiment on the bench, then the platform has a different look where the operator can actually log in, see what is the next experiment, run it on the bench, and then come back to the platform, enter manually the different values that were measured. Once this data is entered into the platform, this has two goals. The first goal is we have a data analytics module that really allows you to see how your experiment performs in real time in your lab. And also this data is then used to be fed back into our machine learning algorithm to retrain it and then suggest what is the next best experiment. And we loop over and over until we reach the target that was designed and set up at the beginning of the whole process. So all of this is packaged into SD Lab. So here you can see two print screen of the platform on the left. So on the top panel, you can see the dashboard that summarizes everything that is happening in your lab, how many workstations are connected, how many experiments are running, the status of those experiments, and so on. And the bottom panel, this is the analytics module where we have automated plots that can be generated really quickly, such as metric scatter chart, violin plot, parallel coordinates, and so on. So we have libraries of different plots that can be automatically generated. The platform offers a menu of different algorithms. So 3 of those are proprietary algorithms. I'll briefly talk about this in a minute. And we also provide other type of algorithms. So we have 10 open source algorithms that are made available to our customers if they want to benchmark or have a feel of how other type of techniques perform on their experiment. Users also have the ability to upload their own machine learning algorithm. So let's say you develop some technique internally, you would like to hook this into the platform. This is something that can be done, and make sure that the algorithm is available only for your team. So this is the first algorithm that we developed. It's called Falcon. It's a general purpose optimization algorithm that can handle any type of variables, let it be continuous, discrete, or categorical. It allows to do Pareto optimization, also known as multiple objective optimization. So typically, if you want to maximize, I don't know, the yield of a reaction, but you want to use as little catalyst as possible because you want to make it cheap. So all these different objectives can be optimized simultaneously. So let me show you some results on how we can accelerate catalysis discovery using our platform. So for here, I'll just take this example, which is a Buchwald-Hartwig cross-coupling reaction. Those are the set of parameters that we can optimize. So here there are different type of precursor for the palladium catalyst, different additives, a set of different ligands. We also want to optimize some process parameters like the time and the temperature at which we want to run the reaction, and also different type of bases. So here we have a nice mix of continuous variables, discrete variables, and also categorical variables. So now if you were to optimize this reaction to find the best set of all these different conditions in order to maximize the yield, it will roughly take 182 experiments in a high throughput screening fashion to maximize the yield of this reaction. So now what if we go with the SD Lab approach where we entirely close the loop and let the system surge by itself? So with Falcon, this will go down to only 30 experiments. So right here, we have a speed up of roughly 6 times. And we can see here in the inner panel where now the number of evaluation that we have on the x-axis is now on the log scale. So we can see that we really have an order of magnitude. So with a high throughput design, we need in the order of the hundreds of experiments, while now with Falcon, you're more in the order of the tens of experiments in order to optimize your reaction. This is also being tested and validated with IBM in a strategic partnership with them, where they have here a ChemSpeed robotic system. They have 6 reactors in parallel, and we optimize 6 reactions simultaneously. It's also a catalyst reaction. We automatically send all the information to this ChemSpeed system, collect all the results to measure conversion and selectivity from their HPLC, put this into our database, retrain the model, and then send the next experiment fully autonomously. But now, so sure, factor 6 in speed up is good, but this is not where we want to stop, because we want to further speed up the discovery. So the question is, what if there is prior knowledge that is available? Because you have a lot of data that you've collected in the past. So can we somehow leverage this? And in the example of the Buchwald-Hartwig reaction, this would be similar to, let's say you've optimized your reaction with 14 ligands, and now you have 1 new ligand that you would like to test. So can we somehow use the information from those past experiments and transfer it to this new ligand? So the answer is yes. I'll show you the speed up that we obtained. And we've done this with our new algorithm called SEMOPT for semantic memory optimization. It's a transfer learning approach based on neural processes. We just published the paper, so you can read about it on the Chem Archive. And the goal is really to enhance the optimization with knowledge from the past, and it integrates with any of the machine learning algorithm that we have in the platform. And this algorithm automatically identify from those prior data what is relevant or not. So at every step, we will have this check to make sure that we don't bias the algorithm to go in the wrong direction. And the goal, of course, is to guide the search directly to the most promising space and avoid those part of the optimization that is irrelevant. So this is what I've shown before. So 182 experiment with brute force, so high throughput experimentation, down to 30 experiment with our Falcon algorithm. So now if we can leverage this data from the past and try to optimize faster this new ligand, then this would be done in only 6 experiments. So right there, again, the speed up an order of magnitude, and compared to high throughput experimentation, this is roughly 30 times faster. Now, also another thing that we've been working on is typically in any type of research, there are a lot of constraints, right? So those constraints could be physical constraint or any type of chemical or physical constraint. So if we think about a reaction, or if you think about a process that has only 2 parameters, let's say temperature and pressure, if you don't specify any constraint, then the algorithm can pick any part of that space and suggest any experiment from that space. But now what if we have some constraint that we know in advance? So typically mass balance constraint. So if you have a vial, you know you need to have only 10 milliliters of it. You have, I don't know, 30 different components that you need to mix together, but you still need to have this maximum amount in your sample. So then this is one type of constraint. It could be also thermodynamic constraint. If you have a reaction, you know, if you put X amount of one reactant, you need to have 2X of the other one. So then you start to build this constraint, and then this space that looks entirely accessible by the algorithm start to have some hole and look a lot like a piece of cheese. And then some of the points that we have identified are now cannot be sampled anymore. So this algorithm that we have been working on is called Emmental, and it allows to do constraint optimization. So it makes sure that the algorithm will not sample area or region of the space that are not allowed because of chemical or physical constraint. We allow a lot of different type of constraint. It can be bounded constraint, relational constraint, or even equality/inequality constraint. So this is the latest development that we've done. And I see Philip is getting the mic. So I won't show this, but here we also have a video. So if you go on the LinkedIn page of the company, there is this video that we just published, and it shows ST Lab in action, where it operates this small prototype lab that we printed. So it's most of it is 3D printed. It has different probes. Here we measure pH, conductivity, and the redox potential. we mix different salt together to come up with an electrolyte for aqueous batteries. And the goal is to let the platform control entirely the system. So this can run 24/7. You can see the probe here is from Mettler Toledo. We connect automatically to this probe to collect all the information and data, populate our database, and then retrain the model and send again instruction to the small prototype. Some challenges, I think we talked about them already. Education, of course, data access. We need to have some standard on the way we can collect information from a lot of different instruments, and also the mindsets, mostly from lab and operators, right? Those are not tools to replace them, but really to empower them so that we can come up with new material much faster. And yeah, I'll stop here. Thank you very much for your attention.
Thank you very much, Loic. I'm not at all a data scientist, but at least I understand why you call it a Menta. Okay, questions? No questions.
Again, to the benefit. I think in case someone is experienced, probably he or she would not do all brute force what is necessary, but says that, I mean, I can also do that faster. What would you answer to that kind of person?
Yes, this is very true. So we also have, so before going there, we also have comparison with DOE for process optimization, for example, where this type of strategy can be easily 6 times, 7 times faster than a regular DOE. We're doing even more benchmark now with different type of DOEs on different set of application to have a better sense of this speed up. But generally speaking, humans are very good at thinking, in 3D, maybe 4D, but as soon as you want to optimize, let's say if you go in biotech and you have a media formulation to optimize, and you have 30 variables, this is extremely challenging for a human to come up with a formulation of all those variables that would maximize some objective. So for this type of application, I think these tools are required in order to navigate this huge combinatorial space.
Thanks, Loic, for a great presentation. One question that Emmental actually brought up for me was, how do you handle things that are maybe discontinuous in your target functions? Like you might have things like phase changes or certain things that happen. In our labs, your algorithms work pretty well, but I think part of the reason why they work and converge so nicely is that we typically have relatively smooth functions where it's reasonably easy to find an optimum, although it's in high dimensions. But when we go to perovskites, for example, I expect that we will encounter phase changes and such things. How would you deal with that?
Yeah, that's a very good question. So let me maybe explain the way we use it, for example, in the catalysis example, or even perovskite example. So the idea is when you have different, if you have different reaction routes, let's say, but you still want to screen your entire library of different catalysts, ligand, or precursors, what you can do is you can come up with ways to define your constraint where they are not continuous at all. So you can say, okay, if I follow reaction path A, I know I cannot mix this type of solvent with this type of ligand. But then if I have reaction B or reaction path B, then actually this type of solvent can mix with this type of ligand. So then the surface is entirely discontinuous. And that's really the goal of Emmental, is to deal with this type of issues where the function itself and the way to sample the function is discontinuous.
Okay, thanks again, Loic. Thanks again, and now we move to another building block which is important for. I think. Sorry, Fedor. I think at least in my conduct it was Tobias before. I don't know if I'm mixing up with the what. Well, we can do it that way. What is your? Okay, so. Okay, it's you. You are right. Okay. No, I totally mixed up my the conduct of the meeting. So sorry. So we go for computational design of materials. Happy to have you with us, Fedor. So Fedor Gumans is the Chief Customer Officer of SCM software for chemistry and materials. The floor is yours.
Thank you, Philippe, and also thank you for the invitation. Yeah, I guess this audience doesn't need any convincing that we need new materials for all the societal challenges, and we need them fast. So we need new materials to harvest energy, store it, use it. We need new processes for clean water. We need better ways of recycling precious materials and so on. And what I will talk to you about today is about what we've been doing at Software for Chemistry and Materials in terms of coming from the atomistic level and our vision as how that will tie together eventually in a more holistic view, integrating also machine learning methods and even robotics in the end. But this is way beyond our expertise, so I'll leave that to others. Yeah, so I'm Chief Customer Officer with Software for Chemistry and Materials. And I just want to give you a couple of numbers from, it's quite an old study actually from McKinsey, but to give you some idea on why this materials discovery in general is too slow. So it takes roughly around a decade to develop a new material into a new market, and even then most of these new materials only give an incremental improvement on the existing ones. The conclusion of this study here was that there's a catch-22, right? So it takes a long time to develop a new material, so there's no incentive to make new materials because it's expensive. So why make a new material if it's not likely to be of any use? And in order to break that vicious circle, if you will, of course, people have been running simulations since decades. You can use that to predict new materials. But inevitably, you still need to make the materials and see if you can use them in the way that the simulations predicted them. So more recently, of course, you get this idea of the self-driving lab, where you can integrate robotics to help you get the simulations, predictions, make them, test them, then in a continuous feedback loop, go up in a positive spiral and find new materials more quickly. And central to all of this is, of course, artificial intelligence, machine learning methods that will help you both to improve the simulation methods, the accuracy and the speed, as well as help you design better experiments more quickly. Ultimately, any type of material is going to have a set of properties which are dictated by what's happening at the atomistic level. So this is where we come from at SCM in Amsterdam. And what we do is we try to develop new methods that allow you to predict properties more quickly and or more accurately, which will help you inevitably to find candidate materials more quickly, but also get a better understanding of why a particular molecular structure or material morphology gives you the desired properties, which can then guide the researchers to search in that type of direction without using artificial intelligence, but by using scientific intelligence. Again, ultimately, one computed material doesn't make a new car. So ultimately, we need to couple these type of atomistic models to the larger scale. How do the materials come together on a device level, right? So let's say a battery, or on a larger level, a car. How does that all work together? And we need ways to make the new predicted materials more quickly and test them in this closed loop that I just showed on the previous slide. Okay, a little bit of background of where we come from. Amsterdam Density Functional is our molecular density functional theory code, which was developed almost half a century ago by Professor Evert-Jan Barends, because essentially there were people doing catalysis, and they wanted to use the computational methods that were developed early on to try and predict and understand how to make better catalysts. So Evert-Jan took methods from the physics community, discretized them, that allowed researchers to use those methods to understand inorganic reactivity. And so initially the code was developed by researchers at the university, PhD students, postdocs, And we were sponsored in the 80s by chemical companies that were eager to come to Amsterdam, learn how to use those methods and take them home and try and make better catalysts from the understanding that they gained. Ultimately, that is not a sustainable academic model because researchers need to produce articles and nowadays get a lot of funding. So we spun off as a company in Amsterdam in 1995 with the idea that by licensing the software, we can continue to develop it and support the users. And that's still most of what we do currently is we develop the software both on our own and in collaboration with partners around the world. And then also support the users so they can use the software to the best use to develop new molecules and materials. Currently in the Amsterdam Modeling Suite, we still center around this molecular DFT code called Amsterdam Density Functional, but we have different methods for dealing with different time scales, mostly still centered around the atomistic level. And it comes with a user interface that can be used both graphically as well from a Python framework, so you can easily set up your workflows together. And there's a central driver, as we call it, that allows you to do interesting things on the potential energy surface, so you can map out reaction pathways, for instance, with any of the methods, atomistic methods that give you forces and energies. And more recently, we've been integrating to larger scale methods, and I'll talk more about that for a few set of specific applications. Okay, so we focus mostly on developing the software and supporting it. More recently, we've been interested in integrating these into multi-skill methods that allow you to develop not only the material or the molecule, but also the entire process or device. And we're definitely integrated in how we can leverage machine learning and materials informatics in that space that will ultimately enable people to develop new materials faster and more accurately. Originally, the software was used, as I mentioned, for catalysis, and that's still one of the areas where it's been used quite a lot, and we're still developing new methods to help the entire process of optimizing a new chemical reactor. But more recently, there's also a range of other applications, and I just want to highlight here batteries, organic electronics, and polymers, where this multi-scale optimization of the entire materials is important. Within the EU, we we're currently leading a consortium called React Pro. So it's a light project in which we try to couple the atomistic methods, accelerate the reaction exploration pathways that we can do at the atomistic level, put that into a kinetic Monte Carlo code called Zacros, and then ultimately, and this is where we are now at the final stages, that will give you a surrogate model in which you can then import that into a computational fluid dynamics code called catalytic foam, which will handle the mass transport, the fluid mixing, as well as the kinetics to do the full scale reactor design. And we're now getting into the final stages that we can actually test that for some industrial test cases. In a more recent project, this is a bilateral project where we're working together with a small Danish company called Hafnium Labs, where we're also focusing on the reactor scale design, but now focusing more on how can we at an early stage find out what kind of reactions can take place, and how can we find out if there's any potential side reactions which are going to wreak havoc if we are going to scale up to the pilot plant or beyond. And so we're working on the automatic side of predicting the side reactions, scaling that into kinetics model, and then finally Hafnium Labs is going to integrate that into their process simulation to find out early on if there's any potential side reactions that need further scrutiny to prevent you from building a reactor that's going to corrode or give some otherwise undesired behavior. All right, now for something completely different, OLEDs. So this is another multi-scale modeling approach that we've been working on, in particular to create a nice set of clean pixels. You need to optimize a lot of materials simultaneously, and within those materials, even different properties. So we can model them at the atomistic level, and people have been using, for instance, our software to understand and predict luminescence properties, charge transfer properties, degradation properties, but that doesn't mean that you then have a good way of finding the next nice set of OLED stacks. So we started a collaboration with a Dutch small company called Symbiont, who are experts in doing kinetic Monte Carlo simulations of excitonic and charge transport properties. But the idea is that we can sort of shortcut all the expensive part of optimizing an OLED stack, so that we can do a sort of a loop where we keep developing new materials and stacks, so we can find the stacks that have the desired luminescence properties, lifetime, and so on, and then focus on the most interesting materials and stacks that you can then test in the lab. And we recently run a couple of pilot projects with European OLED companies, and we find, okay, we can actually predict what they find with a new set of materials, but we still have work to do in terms of improving both the accuracy and the speed, or at least a trade-off in that. So it looks promising, but it's going to be further work to improve that further. Okay, I think key to optimizing both the accuracy and speed is machine learning, and we're currently working on some aspects, in particular using machine learning to make the computational methods that we use faster and more accurate. So we can use machine learning to train force fields, to train electronic structure methods. But what we haven't been working on is what we've heard in the previous talks from CITRINE and ATINARY, is then to leverage that machine learning to do much quicker zooming in on the right kind of space that you want to explore. So yeah, I'd be very happy to see that integrated in the whole scheme of things, where you leverage atomistic modeling, robotics, and machine learning. Before I stop, let me just give you food for thought. So quantum computing is something that we haven't heard before, and probably you will not hear about it for the next decade. But at some stage, perhaps this could be something that can give you really high accuracy, but it's still going to be expensive. So you need to think about, if you want to use this, how do you integrate it into your existing digitalization stack? Okay, let me stop here, and happy to answer any questions.
Thank you very much, Pedro. We have time for one question.
My question, okay, I'm Maye Garter from Techniker and also Secretary of the UMAC platform. My question is, we are participating in EMIRI's project, and my question is for you and also for other colleagues that you can give me the feedback. We are interested to design safe and sustainable materials, like design, and then do you have tools to modeling tools in order to facilitate the design of safe and sustainable materials? In previous, let's say, presentation, I have seen that there are issues to integrate toxicity, but also sustainability. Are you thinking about how this can be done? And concerning quantum presentation, my question is, we have a group in EUMAT platform working in quantum materials, and also we are part of Frontier Commons project in terms of finding the semantic. How could we deal with when quantum semantic ontologies will be different for quantum? Many.
Okay, yeah, so thank you. So many questions. So toxicity, it depends, right? So there's some really excellent QSPR models that allow you to predict toxicity of molecules. If you then talk about, for instance, things like materials and nanoparticles, it becomes a completely different field. And then I think, well, the people who've been talking about using machine learning, they can be much more of help there, using scarce data and then using that. But eventually, you'd still need to test this, right? So if you have a working model, you'd still need to go and do those invasive tests, I guess, in terms of predicting For instance, the LD50 values, these kind of things. Then as sustainability, of course, you can model some aspects of that as well, but you need to define what you want to model and how you can validate the things you get out of the model. So yeah, I'm sorry, it's maybe an evasive answer, but
okay, thank you very much, Fedor. So the next speaker will be addressing a building block of this loop that has not been so much touched. We have discussed about a lot about also validation experimentally, and so this next talk will be about that, a specific tool really to produce high throughput experiments with a new, very innovative approach. So I will let Tobias Koppejans explain you what it is about. So Tobias, I think you are the Chief Operation Officer at VSPARTICLE, which is another nice and very interesting startup in the field.
All right. Thank you very much for the kind introduction and for having me here today. So as mentioned, I'm here on behalf of VSPARTICLE, startup company from Delft University of Technology in the Netherlands. And we started in 2014, about 30 people at the moment. And we focus indeed on a topic that hasn't been discussed that much here yet, which is connecting all of these fantastic digital developments to the physical world, making actual materials and testing those materials and essentially closing the loop. So I have a bit of a technology light presentation because I think we will also start talking about policy a little bit later on. But all throughout the history of humankind, we've been focused on materials, right? From the moment that we've been able to craft tools in the Stone Age, use that to create new materials, all the way to where we are presently, which we can consider the Silicon Age, where we're able to modify materials at the nanoscale. These kind of modifications have led to the digitalization that we see, and computer chips that we can make that way, and all of the spin-out technologies that came from that. But we believe we're also at the brink of a new one that, of course, needs a better name, but ultimately is about reducing our putting the net positive amount of carbon dioxide that we put into the air at zero or very close to that. And that leans on many different technologies that require new materials. Green hydrogen, of course, is an example where you use green electricity and catalysts in order to make green hydrogen. Energy storage has already been touched upon. Batteries, I think, have been a topic here for a while now, as well as carbon utilization. And this technology that you can use in order to reclaim some of the CO2 that we put into the atmosphere and use that to build, to create base chemicals, but at least meaningful building blocks or energy at some point. Now, these things, because they all require new materials, are highly dependent on how long it takes us to develop these materials. And recently, we've been talking to a company called QuantumScape, which is a very well-funded company with the likes of Bill Gates behind it. And they started working on a solid-state battery. And this process essentially took them thousands of design build test cycles over a course of 10 years for them, after burning $300 million, to achieve ultimately lab scale production of a novel solid state battery material. That means that they're now facing the challenge of scaling that up, optimizing that, making sure that it can turn into an actual product, which is estimated to take another 5 years. I've seen a lot of numbers fly by this morning, but 10 to 15 years is definitely in a similar ballpark as what I hear here, which is the time that it takes to develop a new material. Now, if we want to do all these things, the green hydrogen challenge, the energy capture, the CO2 utilization, and we need new materials in order to do that right now, then we have a bit of a problem. And I think that problem is also being discussed here quite extensively, but we are also in part working on this, and the main system that we have developed, and so we're essentially an equipment manufacturer. We sell these devices, sell the technology inside it, is a nanoprinter, a system that is able to manufacture with a single process, a digitally controlled process, many different types of nanomaterials, right? So the focus is nanomaterials, specifically anorganic nanomaterials. You can liken this a little bit to an inkjet printer, which is able to print color photos with just 4 basic colors in the system, where our printer instead uses 62, well, mostly metals, but inorganic elements that you find in the periodic table, and is able to work with all of these and also create mixtures from them. Now, given that the moment you go to the nanoscale, your properties also start to change. So there isn't a single, gold material with constant properties, but everything starts shifting there. All the properties become dynamic. That means that you have an unimaginable amount of combinations that you can create at the scale. And it's these combinations that we're after, trying to unlock this in a automated laboratory. And this printer is for a large part our effort to work on that. So already I think I've seen this cycle appear in various forms: design, build, test, and learn, which is essentially the whole core thing of doing material development. So with this printing system, and I'll give an example in a minute, we aim to not so much reduce the number of cycles that are necessary, which I think a lot of the modeling is about, but we're trying to reduce the amount of time that each cycle takes. In our case, by reducing the amount of time that is spent on material synthesis. Right, so being able to very quickly verify different materials, because at the nanoscale, a lot of these nanomaterials require a specific chemical recipe in order to be made. These chemical recipes are different for all sorts of different materials. So having a single technology that allows you to go beyond these recipes and change compositions just by a digital input is a huge difference. It just reduces the amount you spend on material synthesis greatly. So looking at this case of about 15 years, if we look at what we are doing at the moment, that can fairly easily be reduced to about 5 years. Not by reducing the amount of cycles, but just by making the cycle itself faster. Also means that usually the bottleneck in this process shifts from building to actual testing. We had an example where we were focused on sensors. We're originally building material synthesis was the bottleneck in the process, but where that has turned into testing the sensors, which can easily take days or months. If you combine that with everything that I've heard here this morning about being smarter about how many cycles we can do, we believe that putting this kind of equipment in an automated lab, combining it with AI, with robotics, with smart design of the experiments, you can go far beyond that. You can actually reduce this to about 1 year or so. That's our moonshot, because ultimately we're a startup. We tend to have moonshots. But this is what we're going after, trying to reduce the cycle from 15 years to about a year, so that you can have all these materials quite a bit sooner. So that, I think, is an important part. Here is an example of what we've recently done in the past 6 months. We've used this printing system to tackle the catalyst-coated membranes that are being used for producing green hydrogen. These are usually naphthalene films or some sort of plastic material with, on top of that, an iridium coating. Now, iridium itself is a little bit of a problem because recently, in the Netherlands, we had a little calculation on what it would take to fulfill our green hydrogen ambitions. And that would mean, if you use this kind of technology, that we would need about 25% of the world's supply of iridium. The Netherlands is a pretty small country, so that doesn't scale all that well. So already you can see the effects of that. There is on this graph, there is also the iridium price over the past couple of years, and you can see that already people are starting to realize, hey, iridium is going to be a crucial component here. Prices are going up, and there's quite a bit of volatility. And obviously that's because it's one of the rarest metals on Earth that is every day sinking closer to the core of the Earth. So we thought, hey, hang on. What is important here initially is that we can reduce the amount of iridium that is needed on such a membrane. But in fact, our goal is beyond that, is trying to see out of these many, many combinations that our equipment can make, it is very unlikely that pure iridium would be the very best candidate, right? If you've got billions of different possibilities, why would this one, this pure macro scale compound, be the best solution to that? So you can go beyond it, but initially we started in 6 months to try and reduce the amount of iridium on these membranes. We've been doing that with various institutes, and in 6 months, we've printed, well, hundreds of membranes. and could show there that we can reduce the amount of iridium by 7x. So there's 7 times less iridium on these membranes. And there's potential for more. That's in testing at the moment, where we see that we retain the same performance, which is currently standard in industry. Right, so just by playing with the porosity, with the nanoparticle size, with the layer thickness, and these various properties in the printer, entirely digitally controlled, we're able already to make quite a big dent. Of course, 7x and 25% of the world iridium is still not enough, so we need to go beyond that anyway. But interestingly, we also found that while doing this, we actually took out 6 out of 7 production steps that are involved in making these membranes. Because if you look at that right now, the supply chain is quite a complex one. There is the companies mining the iridium, but then it needs to be processed into a coating, it needs to be applied, it needs to be assembled into a stack, and all these different steps involve different companies. And in fact, the companies that are at the end of the line have a hard time specifying what they actually need from the catalyst. So by bringing all of that a little bit closer together, there's a very interesting use case there. Now, in those 6 months and in the 7 years that we've been working on our core technology, we've also seen quite a few challenges, barriers, and things that are related to this, because ultimately we feel that this was 6 months without doing all of this automated lab experiments, right? This was still manual work on a system that's just very fast at making new materials. If we want to go beyond that, and we've been having that idea for a long time, I want to share a few of the things that we've observed, and also some of the bottlenecks that we've experienced. First of all, as a startup, we feel that really is a valley of death, that that sort of prevents you from successful integration of this whole design, test, build, learn cycle. Integration is usually regarded as, okay, but it's an engineering problem, or it's something simple. While in fact, it's where the real potential of a lot of these technology steps lie. So it's not just about, making, in our case, making this one machine, but really realizing the potential of that machine by also being able to find funding for these kind of integration projects, which are often not understood that well or considered trivial. In part, that is because of standardization, of the lack of standardized and open APIs. So when we designed our system, we made sure that it is completely, for one, it's a digital process, but that is run around an open API. So you can interface with almost everything in the world with that machine, tell it to change parameters or get the data from it. But we find that, for example, with test equipment, this is much more difficult. And we have a hard time integrating with test equipment simply because in many cases there is proprietary software, there are proprietary interfaces, or there is no real path forward to integrate this properly. So that is in part it's standardization, but it's also in part willingness to start and realize the potential of these automated labs. We've also seen, because we have several customers that have been doing research on our technology for a long time, that the reproducibility gains that they get are really good. In general, scientific research has a problem with reproducibility, in part because if you publish results and someone else tries to reproduce it, they need to do the exact same thing. And in many cases, some information or some data is lost there. So, and I think I already saw numbers on this in one of the previous presentations, but essentially this wastes a lot of funding and a lot of time and effort in trying to reproduce results that, where you miss a piece of key information. If you can do automated research, that obviously helps a lot, because then all the steps are traceable and someone else can redo the same work, given the same equipment. Data management is also very interesting. We've met researchers that say, okay, we have to write a data management plan, which for them boils down to, we take all the USB sticks we find in the lab, we put that on a drive, and we make sure there's a backup. And in many cases, that's the scope of what they are going to do. And that is also a little bit of a problem, because essentially it's the institutions, and also the investors and funding agencies that care about the data management bit, right? Being able to tie it together. To make that a researcher's problem, which is the case in many institutions, is a bit of a challenge. So we say, okay, one of the things that we observe is that it would be a very good idea to have institutions do more on data management, not the individual researchers, but have the institutions create the tools. and offer that to them and really drive that and lead that within Europe. And then we also found, and I think I saw that in a previous slide as well, so I'm not saying anything new here really, but funding is too much focused on incremental improvements. Many of the steps in this design, build, test, learn cycle, it's really easy to get funding if you say, I can make a 10% increase, and it's pretty certain that I'm going to achieve it. Sure, you'll get funded. Say, I'll slide a new technology in there, and that has huge potential implications far beyond the 10%. And everyone's like, yeah, but that sounds very high risk. And it's high risk, but in our own experience, where we've shown already for 7 years that this technology works, that we've got a massive burden of proof, that is still the thing that happens most of the time. So this is about being bold, right? Being bold if you're putting out the subsidy programs, being bold as investors, and being bold as multinationals about, hey, let's try something new. Not just reducing the number of cycles, but see also if we can reduce the time that we spend on each cycle. And that's really crucial, because that is, I think, ultimately what this kind of developments and the knowledge that we build around that can put Europe on the forefront of this, because everyone can do incremental improvements, but making massive changes, I think, well, that's up to us. So, any questions?
Thank you very much. Question?
Yeah, so very nice. It's impressive that you could do over 1 billion of different combinations of printing it on the nanoscale. Do you have any information on how well, because of the nano nature of things, that would scale up to a larger scale new material or device?
Sure, that's a good question. I think there are quite a few aspects to that. First of all, this machine produces quantities of material that are relevant at lab scale. That's how it started out. Well, it's not how it started out actually, but it's how we ended up at the device that we're currently at. When we took this technology out of the university, it had been used there for about 20 years or so. And the thing that made us start a company is that it shows a lot of scale-up potential. So this manufacturing method, the synthesis method, does work at scale. It's a process that doesn't really change if you go from milligrams to grams or kilograms. That being said, though, and we tend to focus on where the highest value is in these materials. If you look at pure materials and you break them down into really tiny nanoparticles, then you're adding value nowadays, right? Because you purchase perhaps this rod of iridium at a certain price, but as a catalyst on the membrane, it's worth much more. There are things where technology makes a lot of sense, and there are also things where technology doesn't make sense. We've refrained from putting nanomaterials produced with our technology into paint, for example, because it's just the amount of value added just by breaking it down that much doesn't really work. It also means if you're able to scale with the same technology, that these billions of combinations can be made at scale as well, because we don't change the approach. The technology behind it is called spark ablation. So we create tiny particles by evaporating small quantities of material using a spark. And the key to scaling up for us is twofold. It's making more sparks per second, which goes well for a very long time. And also, because it's a gas phase process, you're able to put many of these machines in parallel. So there's scaling up by numbers, and there's scaling up by the process itself. And that yeah, as long as you stick to products that don't require enormous amounts of nanomaterials, which generally isn't the case, then this approach will scale well.
Thank you. I'm afraid we have no time for additional questions now.